Okay, a logarithmic function is nothing more than an exponent. A logarithmic function is nothing more than an exponent. So, let me give you a function that's in exponential form. Let's say that f of x equals 2 to the x power. And let's say that 2 to the x power is equal to 8. 2 to the x power is equal to 8. Can you solve that equation for me? If 2 to the unknown power is equal to 8, what must the unknown power be?
3.
The unknown power must be 3. This right here, Seth, is called exponential form. To convert, all we have to do first is identify the base. Okay? What is the base in the equation? Well, the base is the part that the power is being raised to. So if I said in this case, Joshua, that the base was 2, does that make sense? I know the base, I know the power. The power is x, and the value or the result is 8. So what I do here, Kate, is I take 2, and I'm going to convert now to logarithmic form. So this becomes the logarithm base 2 of 8 equals x. The logarithm base 2 of 8 equals x. Okay? This little guy right here is called the base. This guy right here is called the argument. The argument. It doesn't mean that he's mad. It just means that he's the value that goes in the logarithm. Okay? So what this says logically is 2 raised to the x power is equal to 8. So this has to be the value of 3. And so that's one conversion from exponential to logarithmic form. Okay? Sydney, whenever I talk about a logarithm, really all I mean is a power, an exponent. So what is the exponent that I'm looking for? That's what I mean by logarithm. Any questions on that so far? Okay, let's look at the following. What if I had 3 to the 4th power equals 81? Well, that's true. 3 to the 4th power is equal to 81. But let's convert this into logarithmic form now. This is currently in what form? Exponential. So let's convert her into logarithmic form. What do we get? Logarithm base 3 81
equals 4.
Correct.
Okay.
This is called the
Number.
argument. This is called the, and even though traditionally in Algebra 2 you would call 4 the exponent, we're going to call it the logarithm. So the word exponent and the word logarithm are synonyms. Exponent is synonymous with logarithm. They're synonyms. Synonyms. There we go. Okay. All right. What if I take 2 to the 0 power? What do I get? 1. So now let's convert this. Let's convert this into logarithmic form. What's the logarithmic form of this? Log base 2, 1 is equal to 0. And this, Kate, is true for any base. So it no longer matters what base you have. If you have the logarithm base b of 1, you will always get the answer 0. Because what is b to the 0 power? It's 1. So this is true for any base that's valid. Okay? This is one of the properties that you need to know. This is one of the special properties that you need to know.
What's its name?
I don't know as if it really has a name. It's just that if the argument of a logarithm is ever 1, then you'll get 0. Okay? Later. You can name it later. Okay? All right. What if I have logarithm base 3 of 3. Logarithm base 3 of 3. 3 to what power gives me 3? That's exactly right. 1. And so what that means is that if you have any base, it doesn't have to be 3. It could be 2 or 10 or 5 million. If these match, if the base is the same as the argument, then you'll always get a 1. Does that make sense? Okay. All right, let's look at some problems then. Come on. Any day now. Thank you. There we go. Okay, let's take the following. If I had, let's say, logarithm base 64 of 8, what does that equal? Logarithm base 64 of 8.
1/2.
1/2.
Kidding. Really? Yes! This is my calling.
64 to the 1/2 power is the same thing as 8. What is the 1/2 power again? It's something that we're more familiar with.
Oh, it's a square root.
Yeah, it's the square root. So 8 is 64 to the 1/2 power, and that's the same thing as the square root of 64. That's exactly right. Very good. Good job, Seth. Okay. Let's take this. Let's say that I have the following. Yes. Let's say I have logarithm base 11 of 11 to the 7th power.
Well, 11 over the 11 is 1, right? And then it's the 7.
So 11, watch where the cursor is right here. 11 to what power gives me 11 to the 7th? 7.
Because you already have 11 to 11.
Yeah. This gives me another property right here, Doris. This says that if I have logarithm base b of b to the r, then the answer is always r. Then the answer is always r. Okay? So this is another property. So right now we have 3 properties that we need to know. So what is the logarithm of 1? What is the logarithm of 1? 0. The logarithm of 1 is always 0. What is the logarithm base 5 of 5?
1.
1. What is the logarithm base 5 of 5 to the 8?
8.
8. Good. There you go. You got it. Okay. Come on. Man, the text file is just too big. It's not anything useful yet. Let's see. Okay. What I want to do here is I want to solve. Okay. We are, and then you have to be able to tell me what the property is that allows me to get rid of the logarithms. Well, we've actually had this property in the previous lesson. The one-to-one property. Yes. So because of the one-to-one property, we can now drop the logs. So 5x plus 1 is equal to 2x plus 10, and now we begin to solve. This is now just an algebra 1 equation.
Would you want us to tell you the one when we get rid of our logs?
You can probably expect to see a question on a quiz or a test that says, why am I allowed to drop the logs here?
But we don't have to write
When you're
it out
actually
there.
solving it out, I don't care whether you tell me or not.
So what's the case when like you can't Just drop the lots. There's like a number in front of the lot.
Yes, I will show you that. We're not quite there yet, but yes, there are several situations. So are we agreed that x has to equal 3?
Mm-hmm.
What you have to do, Caitlin, you have to take your value that you get and you have to plug it back into the original. Okay? Everybody needs to do that. Because when you solve a logarithmic equation, you can pick up what are called extraneous solutions. An extraneous solution is a solution that worked algebraically, but it does not work in the original equation. We're not in any danger here, though. When you plug 3 in here, 2 times 3 is 6, plus 10 is 16. 5 times 3 is 15, plus 1 is 16. Does the log of 16 equal the log of 16? Yes. So we're safe here. But the thing I'm trying to teach you is that anytime you solve a logarithmic equation, you must check the answer back in the original equation. Okay? So that you need to know.
So if it doesn't work in the original equation,
Then it's an extraneous solution and you can throw it away.
So to say like no solution.
Well, that solution doesn't work.
Okay.
You may have one that does work because sometimes you'll solve a logarithmic equation and you'll have 2 answers. But if you have both of them don't work, then you're just going to say it doesn't work. Okay? Now, what do we call the inside of the logarithm again right here? What do we call the x right here? We gave it a special name. Argument. The thing that I need to teach you is that the argument always needs to be greater than 0. You can never have a negative argument. You can never have a negative argument. Now you need to be careful about assuming that the moment you see a negative that it simply won't work. For example, this is a perfectly valid function right here. Logarithm of negative x. It's perfectly valid because there are values of x that I can plug into this. Negative numbers, right? Does that make sense to you?
Yeah.
See, if I let x equal negative 10, then this becomes the logarithm of negative 10, which is 10. And what's the logarithm of 10? The log of 10. 1.
Why?
Yeah, why? It's understood that if you don't have a base here, that the base here is 10. There's one logarithm I haven't written yet, and it's this. This is a special kind of logarithm.
Is that a 1 or something else?
That is an ln. This is called a natural logarithm. This right here, does anybody know what the base is assumed to be, even though the base isn't written? E. The base is E. That's exactly right. Now, what is the natural logarithm of 1?
Zero.
What is the natural logarithm of 1?
0.
It's 0. Because e to what power gives you 1? Well, it's still 0. Now, I'm going to try and do this over a couple lessons, Seth. I just want to demystify this. E is just a number. That's all E is. 2.7, 1828, 1828, something, right? It's kind of like pi. It's related to pi. Whenever you see E, it's just a number. It's a real number, okay? Natural logarithm of E would be equal to what? Correct. 1. Because the base is E. So E to what power gives you E? It's got to be to the first. What's the natural logarithm of E to the 5th?
5.
5. So all the properties that we learned before still work here. The only difference between this and this is that the base here is E and the base here is 10. That's the only difference, Sydney. And the reason why they gave it a new name was because right here, we already don't write the 10, right? So we need some way of writing out a logarithm where we don't write out the E. Well, LOG is already taken. And since E is considered the natural number, this is considered the natural logarithm.
So if something, pretty much if anything in math is natural, then it has to do with E.
A lot. Yes, if it's natural, it has a lot to do with e.
Okay. Would you say with the log x?
Right here, the 10 is not written,
Okay.
so it's log. But the natural logarithm also turns up a ton in the sciences. So we just don't want to write the e. Why? Well, we're lazy. Well, I could write this. Log e x, and that right there, Abby, log base e of x, is the same as this guy. Exact same thing. But I don't want to write the e because this pops up so many times. So what we do is we give it a special name. We call it the natural logarithm, or ln, which is on your calculator. So look at your calculator real quick, and it is right here. There's your ln button. Okay. Here's another property. If I have 5 raised to the log base 5 of 7,
Oh, I remember this kind of.
whenever the base matches the base of the logarithm,
It's just log 7.
the answer will be just what's inside the log.
Oh. Because it's just like your base.
Correct. So if you have b raised to the log base b of 9,
Ooh, 9.
you get 9. If you have e raised to the natural log of 3x,
Okay.
you have 3x. Because the base here is the same as the base here. That's exactly right. Okay. Using the one-to-one property, we've done that. It's 43. Okay. All right. Here's the graph of logarithm base A. Right here, Caitlin, we're assuming right now that the base is greater than 1. Okay. There are some key points that you need to know here. The first key point is that the logarithm crosses the x-axis at 1, 0. The basic logarithm. Okay? Now, if you do transformations on it, that can change, right? But the basic place where it crosses is 1, 0. The domain is from 0 to infinity, and the reason why it can't be anything less than 0 is something I've already told
Can't be
you.
negative.
What can't be negative?
The base, the A, whatever that's called.
The argument.
Argument.
The
No,
argument
that's the
can't be
X.
negative.
Then-
So x can't be negative. The function is always increasing, so it's always rising up from left to right, Joshua. It is a one-to-one function, so it passes the horizontal line test, which means it has an inverse. And instead of a horizontal asymptote, it has a vertical asymptote. At what value? Where is that vertical asymptote? At 0. That's exactly right. So remember, you can't plug in 0 into a logarithm, right? If you haven't written this down, write this down now. Logarithm base b of 0 is undefined. There is no real number that goes with the logarithm base b of 0. That's the same thing that's true for natural logarithm, because the only difference between this guy and this guy is the base. The base is e, right here. Okay? So as x goes to 0 from the left, watch the cursor right here on the board, as x goes to 0 from the left, the function goes down, 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 down. So the logarithm goes to negative infinity as x goes to 0 from the right. As I go this way from the right, the function drops. Okay? Logarithm base a of x. Let's convert this into exponential form. If this is equal to y, how do we convert this to exponential form? A,
into the y equals.
correct.
And he when the y like equals r, I
Mhm.
put it on
Okay.
the right.
All right. What form is this called again?
Logarithm.
And what form is this called again? Exponential. The logarithm, Sydney, is the inverse of the exponential. They're inverses of each other. So if I have f of x equals a to the x, then the inverse function is equal to the logarithm base a of x. They're inverses of each other. Okay, let's talk about translations, shifting. So let's look at the first one right here. The graphs of each of the functions is similar. So here's the parent function, log base x, and I didn't write anything down here, so what do we consider the base to be? 10. Now, what we're going to do here, Seth, is we're going to create a new function g that's equal to the logarithm base 10 of x minus 1. What's the transformation that's happening here? Right 1 unit. To be up 1 unit would have to be what? On the outside of the logarithm. So this is 1 unit to the right. So what happens here, Seth, is all of the key points change. So the key point of 1, 0, where it hits the x-axis, now becomes 2, 0. And the vertical asymptote, which used to be at x equals 0, is now at x equals 1. So this translates over, and this becomes the new vertical asymptote right here. Does that make sense? Okay. Let's look at part B. What kind of transformation is happening here? Upwards 2 units. Is that going to change the vertical asymptote?
No.
No. Because if you go up 2 units with the original graph, the vertical asymptote would only move up 2 units. But since it's a vertical line anyways, moving a vertical line up 2 units doesn't shift the line at all. So the only thing that changes is what? The key point of 1, 0 now becomes 1, 2. And that's why we study key points, by the way, Abby. Key points help us graph the functions when we transform them. Okay? Does that make sense? Okay, natural logarithm we've already talked about, but I just want to make sure this gets in the video. Whenever we say ln of x right here, Joshua, we mean the exact same thing as if we were saying log base e of x. X is the argument, and the argument must always be positive, whatever the argument is. So this is called the natural logarithmic function. Evaluating the natural logarithmic function is easy cheesy. So let's just do d. Let's take the natural logarithm of 1 plus square root of 2. All you have to do is hit the ln key. ln 1 plus square root 2. Close, close. Enter. Which means that e, what does this mean again? Let's talk about the interpretation. E raised to this power right here is equal to what? Let's talk about what the interpretation is. What's the base of the natural log? E. So what we did, we calculated it, right? We took the natural log of 1 plus square root of 2, and we got this, right? So if I take e and raise it to the 0.88137357, what do I get? 1 plus square root of 2. That's all I'm looking for. That's the interpretation. You will be expected to know how to interpret, not just calculate, but interpret. So let's just do another one. Let's calculate this. Let's plug in 0.3. So let's calculate the natural logarithm of 0.3. So ln 0.3, close parenthesis, equals. So the interpretation is that if I take what base? e and raise it to the
Nope.
It's the negative one.
-1.203972804, I'm going to get,
0.3.
so let's just check that out.
Wait.
Here's second, go ahead.
Can you have that kind of negative?
Oh, absolutely.
Okay.
Now it's the argument that can't be negative.
Oh,
The argument here is what?
Negative
Wait.
3.
0.3. So Abby, what I'm going to do now is I'm going to take e, raise it to this power, which by the way is going to be second answer. It's stored in answer. So I'll just do that. And when I calculate it,
Wait, how'd you do that answer key?
Second.
right above the negative sign is ans.
Okay.
And ans is a variable which stores the very last calculation that you did. So right now that I calculated this, ans is equal to 0.3. And it's a shortcut key that allows me to keep from having to type in a whole ton of decimals if I did a calculation. So it's a nice shortcut key.
It is.
Okay. How are we doing so far?
Great.
Make a sense?
Yes.
All right. Look at part A right here. What is the natural logarithm of 1 over e?
1.
-1. Because
Yeah.
1 over e can be written as e to the -1, right? And if you have the natural logarithm of e to the -1, that is the same as -1. That's what we call the inverse property. All right, how about e to the natural logarithm of 5?
5.
5, that's exactly correct. Now, this one's a little bit, maybe not. What's the natural logarithm of 1 divided by 3?
1.
0.
It is 0. That is correct. What is the argument? What is the argument of the natural logarithm?
1.
It's just the 1. It's not 1/3. So this is not the natural logarithm of 1/3. This is the natural logarithm of 1, then divide by 3. And what is the natural logarithm of 1? It's always 0. So this is 0 divided by 3. This is going to be the most common mistake that's going to be made. It's going to be a fact. You're going to view something that looks like this. I'm just going to write a number now. And usually the mistake that happens is students view this as the natural logarithm of 5/8, and that is totally not correct. This is the natural logarithm of just 5, then divide by 8. Okay? So what you can't do, what you have to resist the temptation to do, is you can't just put something that's in a denominator like this into a logarithm.
What would the answer be?
Well, in this case, I just chose numbers, so you'd actually have to plug natural log of 5 in your calculator. So I would do ln 5, close parenthesis, then divide by 8. It's nothing we could do in our heads.
Right.
So then I'd calculate. So it turns out that this is equal to 0.201179. But now let me just calculate natural log of 5/8 real quick. Natural log of 5 divided by 8, we're going to get a completely different number. So now you can see from the calculator that these two values are not the same. Okay? And you've got to resist that temptation. Another temptation is that if you have the natural logarithm of 5 divided by the natural logarithm 8, I don't know how many times I've seen people say, well, that's the natural logarithm of 5/8.
A lot of times. Oh, it's really.
You having
You
fun
feel
with
stronger about this
that?
And it's a vampire.
Okay? You've got to avoid that temptation. You can't take a natural logarithm in a numerator divided by a natural logarithm in the denominator and say that it's the natural logarithm of the two. You've got to learn how to avoid that, like the plague. Okay? Just avoid it. Say no to drugs, say no to that.
So you just find the natural logarithm of 5 and then the natural logarithm of 8.
And then you divide the two. That's exactly right. All right, what's 2 times the natural logarithm of e?
2.
2. Because the natural logarithm of e, what's the base of the natural logarithm? e, and if the base is the same as the argument, then it's what value if the base is the same as the argument? It's 1. So this is 2 times the number 1, which is just 2. All right, when you're finding domains, you're only looking at the argument. Okay? Now again, the argument has to be what? Has to be positive. Can't be 0, can't be negative. So all you have to do to figure out the domain is to make the argument greater than 0. So x minus 2 becomes greater than 0, which means that x is larger than 2, right? So the domain of this logarithmic function here, Sydney, is from 2 to infinity. Does that make sense? Now right here, Seth, there's a transformation on this function. What kind of transformation is it? On part A. To the right 2 units. What does that change for the key points? What key points change then? There's no there's an x-intercept, but there's no horizontal asymptote. It's a so what does the x-intercept become if it goes to the right 2 units? 3, 0. It was originally at 1, 0. Now it's 3, 0. That's the key point of the natural logarithm, and I'll show you why. The natural logarithm of 1 is what? 0. So that's the ordered pair 1, 0. Right there. All right, let's look at this one. Again, now, what's the argument for this logarithm? It's just what's inside. So 2 minus x. So you have to make this greater than 0. So 2 minus x is greater than 0. And when you solve this, you'll add x to the other side, which means that x has to be less than 2. Less than 2. Does that make sense?
I think that's...
So that makes the domain negative infinity to 2. Negative infinity to 2. Does that make sense? So here's the graph right here of the natural logarithm of 2 minus x. All it did was it still shifted it 2 units to the right, right? But because of the negative right here, Caitlin, in front of the x, it did what kind of a reflection? Across the vertical asymptote. So it reflected it this way. Okay? And then the last one, what is the argument of this logarithm here? X squared. So you take x squared, make it greater than 0. Well, that happens in a lot of places. As a matter of fact, there's only one place where x squared is not greater than 0. At 0 itself. So that means the domain of this function is all reals except the number 0 itself. So this is a double reflected function right here.
What?
Goes like that. Okay. Good. Okay. That is the part of the lesson that we're going to do today.